Okay, hello world, hello early birds. So I'm trying to present today time traveling for 886. So I'm Fred Marmond, I'm working on Tetran, and the product is REVEN Axion. It's somewhat commercial talk, but in fact it's, let's see it, state of the art. So so you have a vision of what is using, what tool can be used for this. Reversers and fuzzers have some problems, especially if you have a bug and you want to time travel to see where the bug comes from. If you have some things that are highly obfuscated, and I have some anti-debug tricks. If you are things that are very random, etc. And so developers have the same problems in other boundaries. So we see that current state of static analysis and dynamic approach are great, but not enough. So we propose something else that will help to cover the whole perimeter. I have some screenshots because the product is huge and it will be easier. This is a timeline, so you can, in fact, record the trace in the hardware level, in the hypervisor. Then we can replay the trace. Oh, I don't know if you can read, but it's assembly here. Okay, so this is a timeline. You can click where you want. In 20 milliseconds, you have the full CPU memory at every point. How? It's not full HDMI. You crop pixels. Yeah. So if you want a demo, I can make a real demo in my laptop or in a room over there. So you have here some call stack from REN 3 to REN 0. Yes, you see we have libc kernel and instruction accuracy. You can reverse things about, imagine you have a kernel crash, carbon check is here. You can time travel. We have access to every read, write, execute at the physical level. So we can select any mini memory you want and see in the past or in the future you has been or will read, write, execute some bytes. I hope you can read something on the screen. Of course, we have data centers, so you can select some register, memory, whatever, and see where it comes from or what will be used later. So you can paint the data and the dump registers and assembly. You also have painters with graphs, so you can directly see what the path data took. Of course, you can see the frame buffer computed by your simulator. And we integrate with other tools, IDA, Wireshark, GDB, volatility, KD, etc. For example, here we have from the trace record in the hypervisor level, we generate pickup in Wireshark. Then you can click in the trace, in the network trace, and it will synchronize in the CPU trace because we see DMA, IRQ, PCI access. So you can synchronize things. If I have time, I can show you a demo, live demo. Yeah. So, yes, you can read things. This is a record of, this one is BSOD. This is a kernel bug found by Joru last year. As you can see, I can click and time travel in time. So we have, I should have took my mouse. Backtrack here is huge. You can see that I have the CPU at every point. If I want to see my bug check, with typo. Bug check. Okay, we found bug check here. I can go to bug check and find the code here says that there is a stack cookie kernel overwrite. I can go backward in time. This is every instruction executed by the CPU, so it's linear in time. It's not static, like I used to see in IDEA. So I can go backward and select my, for example, my cookie, turn backward to see where I come from. Okay, so we highlight. I can also tent graph, the same thing. So I can easily see where my cookie come from. And there, you see it's a BP, I don't care, so I can fold this path and follow my data. And in fact, in a full demo, I can go from the kernel crash up to the origin of the bug in the user space. So go back to well, I can do this, in fact, if I have time. So I follow my memory. This is a crash came from, okay, so this is the MoveS. Here we see, I go back in time. I was here, now I'm here in time. And at this point, I have a move. And if I dump the memory, this move is the original font file, with where I see my tainted data from the kernel crash. So you see in perhaps 10 seconds, I found the origin of the crash in my, and I have the full path of the crash between my font file to the kernel crash. So it's time traveling. Of course, I can show the frame buffer that is computed by the simulator. First, I install the font, I click to enter, and I record the trace from this point. And then there is the combo bytes disappear, and the crash comes here. And I can see afterwards all the, if I hide my window, I can find things about, for example, VGA, because when you have the blue screen, in fact, kernel mods can go to the very old VGA mode with 4 bits plain. And so this is all the VGA accesses. If I had time for a second demo. This is a network trace. Okay. So I'm starting my trace when I hit enter on my URL here. And by the end of the trace, we have loaded the page. And if I want to see network accesses, device Ethernet card. I can iterate on my results. I see there are PCI access. Perhaps you can't read, but in a full HDMI, full high definition level, you can see PCI access to physical memory. And in fact, from this trace, we generate by a Python script the pickup. You see that there are some problem in the protocol because the checksum is computed by the network card and not by the CPU. In fact, we record things between the hardware and the CPU MMU. So if you record the trace, network trace in the RG45 and see the difference, you see that the network card in itself is doing some stuff. And if we click on some packets, in fact, we synchronize with the CPU trace, and you see this widget is time traveling from data. In this packet, I receive my system receiving some network packet. So the network card receives the packet, write by DMA to the memory. So this is a PCI write to the memory, and then I can time travel and see where the system will read those memory. And we see that is if I hide this and go to my backtrace, we see where this packet is read. And we have, of course, IRQ, so timers, network, page fault, etc. So we can go to the under page fault and see by the end of the page fault the IRET that will go back to the while that interrupt. So in fact, it's very useful for reversing drivers, building drivers, reversing highly obfuscated code, because imagine you have something very cryptographic. You may have all this part will be cryptographic. Just go by the end of the crypto, and you have the encrypted code or things. So if you have anti-debug tricks, you just have to go after the debug trick, because we're not a debugger, we are a CPU. Yes, I should have started from this. We record the trace at the CPU level, so we are a CPU simulator. We record the trace real time on a hypervisor. Then we replay this trace on our simulator that will generate a huge database that we can use real time. I can speak for hours if you want, but I don't know. So perhaps just my last slide. If you have questions. I'm sorry, I'll speak slowly because my English is terrible.
How much overhead do you see, especially with respect to I/O? And I guess how much data does this generate as it's running?
It depends on what we're recording. In fact, when we record, we are at the hypervisor, and we have a slowdown of system from 5 to 10%. So you can play a movie, move the mouse, etc. The recording itself is very lightweight. Then there is a huge offline processing to generate the database in your simulator. And it may take seconds, minutes, hours, days, but it's offline. So, for example, if you plug a product behind your fuzzer, you have automatic fuzzer that finds things. The recording and the processing is automated, so it's offline. Maybe you don't know it's working, and then you come in the morning and see the projects that are ready to read us. So it saves time to people who work with fuzzers. And the average of the database size depends on the I/O. If you have heap spraying, you are writing a lot of things in the memory. So the database will be huge because we track everything.
So when will this be released? And is there a repository link?
Sorry.
So when will this be released?
Sorry.
Yeah. When is this being released? Are you releasing this open source, or are you going to release this?
In fact, it's used for years by clients, which are many governments, and we are today starting to advertise civilian companies. It's a commercial product because it's 8 years R&D for 10 engineers. We are a small team, but I think everybody knows that engineers have to be paid by the end of the month, and we'd like to be open source, but for now we have not found a business model for open sourcing, so it's a commercial product. And yes, we have it's documented, commercially support, and we have a strong R&D and strong QA, quality assurance, so it's a quite reliable product and not a proof of concept, open source, and do it by your own. So it's something usable for people who want to have the benefits and don't have time to play with things. Yeah.
Do you support SMM execution and to be able to get SMM trace?
Not yet.
Okay.
Yeah. For now, we are at the hypervisor level and we don't support VMX. So you can't see for now the hypervisor inside this and not the SMM. So we are down to ring 0. Yeah. So I'm open here for demo if you want to play with the tool. There is a room over there. Yeah. Thank you.